Good morning all of you. In the last session I had completed your first unit of your module 4, that is stresses in rigid pavement. Okay. In today's session I'll start with your unit number 2 of your module 4, that is design of rigid pavement. Okay. In today's session mainly I dealt with design of, that is thickness of CC slab. Okay. The following sections, okay, I'm going to explain how to design the dowel bars and tie bars, that is a reinforcement of CC slabs. Okay. Design of rigid pavement. Okay. In this unit, okay, we are going to concentrate mainly on 3 parameters. One, it is design thickness of CC slab, design thickness of CC slab. Second one, it is design of dowel bars, and third one, it is design of tie bars. Okay, the dowel bars and tie bars are the reinforcement they are going to provide in the CC slab. Okay, the dowel bars usually provided, okay, across the transverse joints. Across the transverse joints, the main purpose of providing dowel bars is to transfer the partial amount of wheel load from one slab to another slab. That is particularly for the adjoining slab. Okay, the dowel bars will be transfer the partial amount of wheel load. Okay, suppose if it is about 5000 kg, if it is about 5000 kg of wheel load will be acting on the CC pavement, out of that 5000 kg, if it is maximum about 40%, we can say, that is 2000 kg, okay, your dowel bar system means whatever the total number of dowel bars we are going to provide across the transverse joints, no, okay, those dowel group will transfer about 40% of the acting wheel load to the adjoining slab. That is the main purpose. Okay, transfer the partial amount of wheel load to the adjoining slab. Okay, and tie bars. Okay, these are the reinforcement which is provided across the longitudinal joints. Okay, dowel bars across the transverse joints. It may be a contraction, expansion, warping, or construction joints. Okay, tie bars will be across the longitudinal joints, and the main purpose of providing tie bars is to arrest the cracking along the longitudinal direction, and also, okay, to prevent the separation of adjoining slabs or adjoining lanes, we can say, to prevent the separation of adjoining lanes. Okay, the design thickness means what is the thickness of CC slab? Okay, the thickness of CC slab we are going to design it. Okay, in your semester end examination now, okay, in your semester end examination, they may ask the numericals on design of thickness of CC slab, design of dowel bars, and design of tie bars, or they may also ask the design procedure. They may also ask the design procedure as per IRC 58/2002. As per IRC 58/2002. Okay, in today's session, I'll deal with your first concept, that is design thickness of CC slab. Okay, in the following sessions, okay, I'm going to explain how to design the dowel bar and how to design the tie bars. Okay, next it is numerical problem on thickness of CC slab. Numerical problem on thickness of CC slab, that is cement concrete slab. Okay. The first problem it is design a cement concrete pavement for the following conditions. Design wheel load 4100 kg, present traffic is 300 commercial vehicles per day, that is 300 CVPD. Then design life is 20 years. Then traffic growth rate is 7.5%. Then temperature variation is 13.1 degrees centigrade, and modulus of subgrade reaction is 6 kg per centimeter cube. Then concrete flexural strength, it is 40 kg per centimeter square. Then modulus of elasticity of concrete E is 3 into 10 power 5 kg per centimeter square. Poisson's ratio of concrete mu is equal to 0.15. Then coefficient of thermal expansion alpha is equal to 10 into 10 power minus 6 per degree centigrade. Okay, these are the given data. Using these data, you are going to design the thickness of CC slab. You want to design the thickness of CC slab. Okay. Okay, go for the solution. Okay, in the first step, you need to select a trial thickness and the spacing of longitudinal joints and transverse joints. You need to select a trial thickness along with the spacing between the transverse joints and longitudinal joints. Okay. First, select a thickness of 20 centimeter transverse joint spacing is equal to 4.5 meter and longitudinal joint spacing, or we can say lane width, it's about 3.5 meter. Okay, the transverse joint spacing and longitudinal joint spacing or lane width, okay, have selected as per the IRC recommendations. As per the IRC recommendations means, first in the first step of design of CC slab thickness, first you need to select a trial thickness and you need to assume the transverse joint spacing and longitudinal joint spacing as per IRC recommendations. Okay, so in this case, okay, I have assumed the thickness of 20 centimeter, transverse joint spacing of 4.5 meter and longitudinal joint spacing of 3.5 meter. Okay, Lx, Ly, or we can say L and W. Lx, Ly, or we can say L and W. Longitudinal spacing is L and lane width is W or Ly. Okay, once you assume the transverse joint spacing and longitudinal joint spacing and you have selected a trial thickness, then you need to find the radius of relative stiffness. Radius of relative stiffness. We have radius of relative stiffness L is equal to EH cube 12K 1 minus mu square to the power of 1 by 4. Therefore, L is equal to E is 3 into 10 power 5, H is whatever the thickness you have selected, no? That is 20 centimeter, that is 20 cube divided by 12K, K value, the modulus of subgrade reaction they only given, it is 6 kg per centimeter cube, 6 multiplied by 1 minus mu square, mu is 0.15. Okay, substitute it and get me the value. How much it is? It's about 76.42 centimeter. 76.42 centimeter. Is it clear? Okay. This is the first step in the design of thickness of CC pavement. Okay. You need to select a trial thickness and assume the spacing between longitudinal joints and transverse joints. Then find the radius of relative stiffness L. Okay, you have got about 76.42 centimeter is your radius of relative stiffness. Okay, in the next step, you need to find the temperature stress at the edge region using the chart. Next step is you need to find the temperature stress at the edge region using the chart of IRC 58/2002 page number 21. Is it clear? Now L by L, it is L is 4.5 meter, no, that is in terms of centimeter is 450 centimeter divided by 76.42. L by L is how much? We got about 5.9, and W by L or Ly by L, W by L or Ly by L, that is 350 divided by 76.42. How much you get? This is about 4.6. Okay. See here, from IRC 58/2002, IRC 58/2002, page number 21, okay, for L by L is equal to 5.9, for L by L is equal to 5.9, the coefficient C is equal to, how much? So, you may see here, this is a coefficient chart as per IRC 58/2002, okay. For the L by L ratio of 5, you may have 0.720, and for the L by L ratio of 6, we have 0.920. Then for the 5.9, it is between 0.720 and 0.920, no, interpolate it for the 5.9. For the 5 it is 0.720 and for the 6 it is 0.920. So interpolate it for 5.9. What is the value? Okay, it's about 0.9. It's about 0.9. Okay. Next, from temperature stress chart for edge region, from temperature stress chart for edge region, that is also there in your IRC 58 page number 21 only. Okay, you may see here, this is the temperature stress chart particularly for the edge region. Okay, in the x-axis we have the temperature differential delta T in terms of degree centigrade, and in the y-axis we have, okay, edge temperature stress in terms of kg per centimeter square, and whatever the curves is there, those curves are for the respected coefficient values from 0.1 to 1. There are about 10 curves now from 0 to 1, 0, 0.1, 0.2, 0.3, like that. Okay, using this chart, okay, you may obtain the edge temperature stress, that is temperature stress at the edge region. Okay, so we have 0.9 as your coefficient C, and they only given the temperature differential of delta T 13.1 degree centigrade. Okay, go for the your edge stress chart, edge stress chart. Okay, in the x-axis for about 13.1 degree centigrade. Okay, touch your 0.9 coefficient curve. Okay, from an x-axis of 13.1 degree centigrade. Okay, draw a vertical line parallel to y-axis till that line touches the coefficient curve of 0.9. From that point, draw a horizontal line parallel to x-axis till that horizontal line touches the y-axis. Okay, at that point where the horizontal line touches the y-axis, no, at that point note down the, okay, value of temperature stress at the edge region. Okay, for delta T is equal to 13.1 degree centigrade and C is equal to 0.9. C is equal to 0.9. STE is temperature stress at the edge region. How much it is? Refer it. 13.1 and 0.9 C curve. Okay. How much you get? It's about 18 kg per centimeter square. Temperature stress at the edge region using the temperature stress chart at the edge region. Okay, you may get about 18 kg per centimeter square. Okay. Next, once you get the temperature stress at the edge region, okay, then you need to find the residual strength of concrete. Means, what is the strength of concrete remaining in concrete after subjected to a temperature stress of 18 kg per centimeter square. Okay, the residual strength of concrete is the one. What is the strength remaining in the CC slab after your CC slab is subjected to a temperature stress of 18 kg per centimeter square? That is the residual strength of concrete. Okay. This is second step. In the third step, you need to find the residual strength of concrete. Residual strength of concrete. Okay. Usually, initially, what is the flexural strength of concrete? We have about 40 kg per centimeter square. And what is the temperature stress at the edge region? It is 18 kg per centimeter square. Okay. Then the remaining is the residual strength of concrete. Okay. Residual strength of concrete is equal to flexural strength of concrete. Flexural strength of concrete minus temperature stress at the edge region. Temperature stress at the edge region. Okay, the flexural strength of the concrete they only given, that is 40 kg per centimeter square. Okay, and the temperature stress at the edge region. Okay, in the previous step we have find out that, okay, about 18 kg per centimeter square, that is STE. Okay, it's about 18 kg per centimeter square. Then 40 minus 18. Okay, you may get about 22 kg per centimeter square. Okay, 22 kg per centimeter square is the residual strength of concrete. Is it clear? Okay, this is the third step. Okay, in the fourth step, we need to find the wheel load stress at the edge region. Okay, from IRC stress chart. In the fourth step, you need to find the wheel load stress at the edge region from the IRC stress charts. Okay, see here. For H is equal to 20 centimeter, K is equal to 6 kg per centimeter cube. Okay, and the wheel load they are given, it is 4100 kg, no, and then axial load is becomes 8200 kg, then it is 8.2 tons. Then you are supposed to refer 10-ton chart. Okay, it is a single axial load of 8.2 tons capacity. Then you need to refer the 10 tons, okay, chart. Why? Means 8.2 tons, no. So for the safety purpose, you are going to refer the higher value. Okay. For H is equal to 20 centimeter and for K is equal to 6 kg per centimeter cube, and for the single axial load of 10 ton, for the single axial load of 10 ton, if you refer the IRC 58/2002 appendix 1 chart, for axial load of, that is single axial load of 10 ton, okay, you may obtain the wheel load stress at the edge region. Okay, for H is equal to 20 centimeter and K is equal to 6 kg per centimeter cube. Okay, from IRC stress chart of appendix 1, IRC stress chart of appendix 1, okay, the V load stress at edge region, the V load stress at the edge region SE, okay, how much it is? Okay, refer you. In the x-axis we have slab thickness in terms of centimeters, and the curves are made with respect to the modulus of subgrade reaction. Okay, it is about 5 curves now, 6, 8, 10, 15 and 30. Okay, and in the y-axis we have a V load stress in terms of kg per centimeter square. Okay, for the 20, okay, touch the first curve, that is 6 kg per centimeter cube, 6 kg per centimeter cube. From that touch the y-axis, okay, that is your edge load stress. Okay, how much it is for 20 centimeter thickness and 6 kg per centimeter cube? How much it is? Okay, it's about 25 kg per centimeter square. Okay, 25 kg per centimeter square is the edge load stress, that is V load stress at the edge region. Is it clear? Okay, once you got the V load stress at the edge region, okay, then you need to check the available factor of safety on load stress, available factor of safety on V load stress. Okay, in the next step you need to find the available factor of safety on the load stress. Okay, always that available factor of safety on the load stress should be greater than 1. Okay, then only your selected thickness will be almost finalized. We can't say it is finalized, okay, almost finalized. If it is available factor of safety is more than 1, then your selected thickness is almost finalized. Why I am saying that almost means, okay, after finalizing from available factor of safety, then you need to check for corner load stress, then you need to check for correction based on the traffic data. Okay, then only finalize the design thickness. Okay, okay. Next it is available factor of safety on load stress. Available factor of safety on load stress, that is V load stress. Okay, usually available factor of safety on load stress is the ratio of, okay, residual strength of concrete and V load stress. Okay, it's the ratio of residual strength of concrete and edge load stress, edge load stress, that is V load stress at the edge region. Okay, residual strength of concrete, how much it is? 22, and edge load stress it is about 25. Okay, 22 divided by 25, how much it is? It's about 0.88. Okay, this ratio is less than 1, no, then it is not okay. Okay, if this ratio is more than 1, that available factor of safety is more than 1, then the selected thickness of H is 20 centimeter is almost, okay, the design thickness of CC slab, almost finalized. Okay, since your available factor of safety on the load stress is less than 1, then you have to revise the thickness. Okay, you have to revise the thickness. Okay, means you need to increase the thickness of CC slab. Okay, you need to increase the thickness of CC slab. Okay, select a thickness of 23 centimeter. Select a thickness of 23 centimeter and the spacing remains the same. Spacing remains the same, that is L is equal to 4.5 meter and W is equal to 3.5 meter. So if you select a thickness of 23 centimeter, okay, the radius of relative stiffness L, we have L EH cube 12K 1 minus mu square whole to the power of 1 by 4. Okay, substitute it and get me the value. Okay, E is 3 into 10 power 5, H is 23 cube, 12 into 6, 1 minus mu square, that is 1 minus 0.15 square power 1 by 4, okay, you may get about 85 centimeter. You may get about 85 centimeter, okay, is the radius of relative stiffness L. Is the radius of relative stiffness L, okay. In the revised one also the first step is over. We have increased the thickness to 23 centimeter from 20 centimeter and your radius of relative stiffness increases from 76.4 to 85 centimeter. Once you got the radius of relative stiffness L, then you need to find the ratio of L by L and W by L, okay. Now L by L 450 divided by 85 is equal to 450 divided by 85 is equal to 5.3 and W by L is 350 divided by 85, you get about 4.1. 4.1. Okay. Out of those two, which is higher, that will be considered for the coefficient. Okay. In the previous one also 5.9 and we got about 4.6. No, that's why we consider higher value, that is 5.9. Here also if you consider L by L and W by L, where L by L is more than W by L, that is 5.3. No, okay, that will be considered for the design. Okay. Next, for L by L is equal to 5.3, okay, from IRC 58, 2002, page number 21, refer here, okay. For the 5 we have a ratio of, okay, for the ratio of 5, L by L ratio of 5 we have 0.720, for ratio of 6 we have 0.920, okay. For 5.3 how much you get? The coefficient C, how much it is? The coefficient C, it is 0.77. Okay, 0.77. Okay. Next, for delta T is equal to 13.1 degrees centigrade and C is equal to 0.77. C is equal to 0.77. C is equal to 0.77. Okay, how much you get? Your temperature stress at the edge region. Temperature stress at the edge region. So refer here. In the x-axis we have temperature difference delta T in terms of degree centigrade. Y-axis it is the temperature stress at the edge region in terms of kg per centimeter square, and the curves for coefficient C values from 0 to 1. Okay, we have a coefficient of 0.77 and we have delta T of 13.1 degree centigrade. Okay, refer here. How much you get? That is STE, okay, for delta T of 13.1 degree centigrade and C is equal to 0.77 from temperature stress chart. From temperature stress chart, STE, that is temperature stress at the edge region, is equal to how much? About 15 kg per centimeter square. It's about 15 kg per centimeter square is the temperature stress at the edge region obtained from the chart. Okay. Next, once you get the temperature stress at the edge region, what you need to find? Next is residual strength of concrete. Okay. Residual strength of concrete. Okay, we know that residual strength of concrete is the difference of flexural strength of concrete and temperature stress at the edge region. Okay, we have flexural strength of concrete about 40 and we have 15 is the temperature stress at the edge region. Okay, 40 minus 15, okay, you may get about 25 kg per centimeter square. 25 kg per centimeter square is the residual strength of concrete. Okay. Next, once you obtain the residual strength of concrete, okay, in the next step you need to find the yields load stress from IRC stress charts. Okay, for H is equal to 23 centimeter, for H is equal to 23 centimeter and K is equal to 6 kg per centimeter cube from IRC stress chart, from IRC stress charts, yields load stress SC is equal to, yields load stress SC is equal to, refer your, okay, for 23 it is between 22 24 cent, no, that is mid of 22 and 24 we get the slab thickness of 23 centimeter, for 23 centimeter, okay, at about 6 kg per centimeter cube curve, okay, what is the wheel load stress you got? Okay, it's about 20 kg per centimeter square. 20 kg per centimeter square is the yield load stress. Okay, so once you got the yield load stress, then you need to check the available factor of safety on yield load stress. Okay, next it is available factor of safety on load stress, that is wheel load stress at edge region. Okay, that is equal to what? That is the ratio of residual strength of concrete and wheel load stress. Okay, the residual strength of concrete is 25 kg per centimeter square and the wheel load stress is 20. 25 divided by 20, you may get about 1.25. Okay, it is more than 1, then the selected thickness is okay. Then the selected thickness is okay. Okay, in previously we got about 0.88, no? If you select the thickness of 20 centimeter, how much you got? 0.88, then the ratio is less than 1, the factor of safety is less than 1. Then the selected thickness is not safe. Okay, since in this the available factor of safety is more than 1, then the selected thickness of 23 centimeter is almost okay. Once your selected thickness of 23 centimeter or whatever thickness you have selected is almost okay, then you need to check for corner load stress. Then you need to check for corner load stress. Okay, check for corner load stress. Okay, we have SC is equal to 3p by h square 1 minus a into root 2 divided by L, okay, power 1.2. Okay, always while checking you need to use a modified equation for the corner load stress, it is power 1.2. Okay, and assume the wheel load distribution about 15 centimeter. Okay, calculate it. Therefore SC is equal to 3 into 4,100, H is 23 centimeter square, 1 minus A is 15 into root 2 and radius of relative stiffness we got 85, okay, power 1.2. Okay, how much it is SC? It is about 24 kg per centimeter square. 24 kg per centimeter square. Okay, the corner load stress should be less than flexural strength of concrete, then only your selected thickness of 23 centimeter is safe for even corner load stress also. Okay, since you obtained corner load stress is less than 40 kg per centimeter square, your selected thickness of 23 centimeter is also safe with the corner load stress. Okay, is less than 40 kg per centimeter square, then okay. Okay, in the check for corner load stress also, okay, your 23 centimeter is okay. Is it clear? Okay, next for the correction factor, okay, you need to apply the correction factor based on the traffic volume. Okay, here the initial traffic they have given 300 commercial vehicles per day and traffic growth rate they have given, that is 7.5%, that is annual traffic growth, means per annum there will be increase of 7.5% of vehicles, and the design life they have given 20 years. Using these data you need to find the traffic volume. okay, and with respect to traffic volume you need to apply the correction factor, then only you need to finalize the design thickness of CC slab. Okay, go for that. Once you apply the correction for corner load stress, then you need to apply the correction for check for correction factor. Check for correction factor. Okay, we have design traffic A is equal to P into 1 plus R to the power of N plus X. Okay, where A is the design traffic and P is the initial traffic, that is the traffic data as per last count. They have given, no, it is 300 commercial vehicles per day, that is a traffic data as per last count, and R is the traffic growth rate, that is 7.5% they have given, and N is the design life, they have given it's about 20 years, and X is the construction period in terms of years. X is the construction period in terms of years, means from the last count to the completion of construction. Okay, from the last count of survey to the construction completion, whatever the period in terms of years, that will be X. Okay, usually it is 2 to 3 years. Since they are not given the value of X, okay, in this case you are going to assume the construction period X is equal to 3 years. Okay, assume construction period X is equal to 3 years. Okay, therefore A is equal to 300, 1 plus 0.075, N is 20 plus X is 3. Okay, how much you get? The design traffic 1583 CVPD, that is commercial vehicles per day. 1583 CVPD commercial vehicle per day. So as per IRC recommendation, the correction factor, okay, for the traffic which is about from 450 to 4500 is 0. For design traffic of 1583 CVPD, HT is 0, the correction factor is 0. Okay, then if the correction factor is 0, then it is also safe for your corner load stress, then the design thickness is the selected thickness only. Then the design thickness is selected thickness only, that is 23 centimeter. Okay, last sentence, therefore adopt the design thickness of 23 centimeter. Adopt the design thickness of 23 centimeter. Okay, it's very simple. Okay, what you are going to do? Okay, the steps for designing of CC slab thickness. First, you need to select a trial thickness and assume the spacing between transverse joints and longitudinal joints. Okay, that is the first step. Okay, after selecting a trial thickness and assuming a spacing, then you need to find the radius of relative stiffness L. Once you find the radius of relative stiffness L, then you need to find the coefficient C. Okay, for the L by L value and for the W by L value from IRC 58/2002. Once you find the C, next you need to find the temperature stress at the edge region using the stress chart for delta T and C value. Okay, once you find the temperature stress at the edge region using the stress chart, the next is you need to find the residual strength of concrete. Okay, once you find the residual strength of concrete, then you need to find the edge load stress at the edge region, that is V load stress at the edge region, by using IRC 58/2002 stress chart for the respective K value and the respective thickness. Okay, once you find the edge load stress, okay, then you need to check for available factor of safety on the load stress. Okay, the available factor of safety on the load stress is the ratio of residual strength of concrete and the V load stress. If the available factor of safety on the load stress is more than 1, then the selected thickness is the design thickness. Okay, if it is less than 1, we have to revise the thickness. Means you need to increase the thickness. Revise the thickness means you need to increase the thickness. Again, find the radius of relative stiffness and the residual strength of concrete and V load stress till the available factor of safety and the load stress should be more than 1. Once your available factor of safety and the load stress is more than 1, okay, almost the selected thickness is final. Okay, next you need to check for the corner load stress. Okay, check it whether your corner load stress is less than flexural strength of concrete. Okay, if it is less than flexural strength of concrete, then okay, the selected thickness of 23 centimeter is also safe for your corner load stress. Once your check for corner load stress is over, then you need to check for correction factor. Okay, for the design traffic. Okay, find out the design traffic using the relation A is equal to P into 1 plus R to the power of n plus x. Using that, find the design traffic. Okay, with respect to design traffic, find the correction factor. Okay, if any correction factor is there, apply the correction factor to the selected thickness, then finalize the design thickness. And for this case, okay, we have got about design traffic of 1583 CVPD. No, for 1500 to 4500, the correction factor is 0. Okay, then you are going to adopt the thickness of 23 centimeter only. Is it clear? Okay, this is regarding the numerical problem on thickness of CC slab. Okay.